I am going to present some verification sort of theory and background and verification analyses we've done. And then Joe is going to present sort of the numerical implementation and some applications of Maxwell damping. So Maxwell damping, what is it? It's a new feature in FLAC 3D version 9. Starting with version 9.0, and I guess it's also in FLAC 2D and 3DEC. And it's a form of damping that has a number of advantages over Rayleigh damping. I mean, and probably for most people, the most important advantage is there's a minimal reduction in numerical time step, so it doesn't have this terrible small time step that Rayleigh damping sometimes requires. But in addition to that, the range of almost constant damping, there's for a frequency range over which you have constant damping is much wider than in Rayleigh damping. And then it's also free from these spurious non-physical body forces that are produced by the mass damping part of Rayleigh damping. So in FLAC 3D, Maxwell has been implemented for solid elements, structural elements, and then these link elements that connect structural elements and solid elements. And I think before getting into all the gory technical details, I think it's maybe take a step back and I think give some context. Okay, so what kind of applications are at least we're interested in here for this kind of damping? And at least my group at the core, we're interested in 3D seismic deformations of embankment dams. And all these embankment dams, it's not just soil, they're what we call appurtenant structures. So there's things like control towers, outlet tunnels, spillways, gates, bridges. So there's all kinds of structures there. So these models usually have structural elements. So there's a cell structure interaction component to these analyses. And some of these structural components, some of these dams are really old. So they're sort of delicate structural components. And sometimes the structural analysis is almost the main point of these analyses. First, we'll start by reviewing some of the problems with Rayleigh damping. These are well-known problems with Rayleigh damping. So Rayleigh damping, it's the most commonly used form of damping for time domain seismic analyses. It's a combination of stiffness damping and mass damping. And each of these forms of damping is strongly dependent, but when combined, they provide a frequency band of relatively constant damping, with damping sort of increasing very rapidly out of that range. And as mentioned, the really serious drawback of Rayleigh damping is this drastically reduced numerical time step that the stiffness damping part of Rayleigh damping typically requires. So here's a formula from Belichko, where he's estimating the critical time step from stiffness damping. So the time step, it's a function of omega max. So that's the highest frequency in your mesh. And the typical FLAC dynamic analysis, you're going to have a time step of maybe 1 × 10⁻⁴ or less than that. So that's a frequency of like 10,000 hertz. And it's kind of weird. I mean, that 10,000 hertz, that doesn't really have any engineering significance, but it really affects your time step. And another disadvantage of Rayleigh damping, as mentioned, is this very narrow frequency range of frequency independent damping. And the idea here is that ideally you would have constant damping for all frequencies, because it's been shown that the small strain damping of rock and soil exhibits an almost constant damping ratio of the full sort of observable frequency range. And a less well-known problem with Rayleigh damping is it has these spurious non-physical body forces that it introduces for motion at a constant velocity and other low frequency motions. And that's produced by the mass damping component of Rayleigh damping, which is actually a viscous dashpot connected from each node to a fixed zero reference reference frame. So that's a very unnatural sort of thing that cannot exist in nature. There is no fixed reference frame. So that introduces non-physical drag forces, which can affect results in seismic deformation analyses. All right, so the Maxwell damping scheme, well, first the mass damping is skipped, is ditched, and just focuses on improving stiffness damping. So the idea with Maxwell damping is you replace the dashpot of stiffness damping with one or more Maxwell components, which is a spring in series with a dashpot. And a single Maxwell component produces frequency-dependent damping, peaking at a particular frequency with broad tail. So the sort of the damping response of a Maxwell component, single Maxwell component, is shown here. Again, the idea is, okay, this is stiffness damping over here. You have this viscous dashpot, which becomes super stiff at high frequencies. That's the whole problem with Rayleigh, with stiffness damping at high frequencies. And it's sort of an obvious idea is, hey, let's stick a shock absorber in here, sort of a spring. So we'll put a spring in series with our viscous dashpot, and then a spring in series with a dashpot. That's called a Maxwell component. And I guess I should mention, okay, in all of these sort of spring dashpot models, this main spring, that represents your constitutive model, linear or nonlinear. So that's the response for one Maxwell component. And sort of the full scheme is if you put a number of these Maxwell components acting in parallel, they can be used to produce approximately constant damping over a desired frequency range. So the more Maxwell components used, the wider the frequency range relative constant damping is. So for this example, we've got 3 Maxwell components, and that can give you relatively constant damping between, say, 0.5 hertz and 25 hertz. And for us, for our kind of particular analyses, that's the relevant frequency range for most seismic deformation analyses. And outside of that range, damping gradually drops off, you know. And it's interesting, that's almost opposite to what Rayleigh damping does. Rayleigh damping is goes to very high damping outside the relatively constant damping range. And again, so what ITASCA has given us in the current implementation, they're providing 3 of these Maxwell components, and you, the user, are free to set the frequencies of each of these Maxwell components and the damping of those Maxwell components. So you can sort of, you know, it's a typical ITASCA thing, you're given the basic low-level tools, and, you know, you do what you want with them. And for us, this kind of damping fit works nicely for us. We try to get constant damping between, you know, 0.5 hertz and 25 hertz. But you know, I mean, if your application was, say, you're working on LNG tanks where there's a fluid sloshing mode that has a period of 10 seconds, you might want to shift this whole damping curve to the left, or maybe you want to move one individual Maxwell component to the left. Or say you're working on nuclear power plants where you got all this sensitive equipment in it that's you know, sensitive to like frequencies up to 60 hertz. Maybe you want to move this whole thing to the right, or maybe move one of these Maxwell components to a higher frequency. I mean, it's up to you. You're responsible for sort of designing what kind of damping you want out of this. So just some history and background on Maxwell damping. The idea, you know, as a physical mechanism for frequency-independent damping, you know, which is, you know, been observed in nature, is discussed in standard texts on stress waves and solids and seismology. So these are I mentioned these because these were sort of standard textbooks when I was in grad school at University of Minnesota. They've been sitting on my shelf since grad school. So one of the first applications, I think this is probably the first numerical application of the technique, was this seminal paper by Liu that everybody cites, 1976. They used 12 Maxwell components to obtain almost constant damping over 4 orders of magnitude of frequency. That was a seismology application. But, you know, more recent exploration, geophysics and seismology applications have limited the number of Maxwell components to 2 or 3. There's really some nice overviews of the historical development of this Maxwell damping technique, at least for geophysics and seismology by Bielak. And I want to give a hat tip to Professor Bielak, because he was the first one that suggested that we look into Maxwell damping for FLAC 3D. So I mean, summarize, like, this technique is pretty widely used in seismology and exploration geophysics. So the technique is well established in that. There's decades of experience in that field, but application of Maxwell damping type schemes to civil engineering analysis codes is relatively recent. And even more recent is the use of Maxwell damping for nonlinear analyses. So these, you know, in geophysics and seismology, you're talking about a linear elastic applications, but here we're trying to use Maxwell damping for nonlinear analyses. As far as I know, the only codes that have Maxwell damping for nonlinear models is LS-DYNA and FLAC. Well, and FLAC 2D and 3DEC. So there's always a fly in the ointment. So there's one tricky side effect of Maxwell damping that you have to be aware of analyses, which is that the phase velocity increases with frequency with this kind of model. So here's the frequency increase for a single Maxwell component, and if you have the full scheme with 3 Maxwell components, you have like a almost sort of a constant increase in phase velocity with log of frequency. And I mean, you can actually just inspect, just from inspection of this model, you can see, okay, if this stiffness, if this dashpot becomes infinitely stiff at high frequencies, you can sort of see what the, you can just do a hand count to see what the phase velocity is going to be. So this increase in stiffness and phase velocity with frequency, it's a fundamental feature of linear viscoelastic models, and it's actually a necessary theoretically on theoretical grounds to satisfy causality. So Aki and Richards in their seismology textbook, they have a very nice discussion, sort of, well, accessible discussion, I'd call it, on this whole causality issue. And this behavior is actually consistent with the observed behavior in geomaterials, at least for the very low damping range where viscosity is the physical mechanism of damping. And again, this is something that's not you cannot fix this issue with some different arrangement of springs and dashpots. This is a fundamental issue with linear viscoelasticity. And maybe you're asking yourself, hey, we use stiffness damping all the time. Why have I never seen this? Why have I never run into this issue before? Well, stiffness damping, which is also a linear viscoelastic model, that also has this increase in phase velocity. It's just shown here in this red line. I mean, the issue is it just doesn't really occur until higher frequencies. Whereas for Maxwell damping, it's kind of spread out over a broader frequency range, and at least it's limited. Whereas stiffness damping becomes stiff, very stiff at high frequencies. The sort of practical significance of this phase velocity increase with frequency. So say if it becomes pretty significant at if you're using higher damping. So say you're trying to use 5% damping, your frequency is going to increase over 20% at high frequencies. So that's that's a little bit concerning. But if you're sticking to 1 or 2% Maxwell damping, then the increase is much, and phase velocity is much more contained. As from a geotechnical engineering perspective, that doesn't seem like such a big deal to me. So for 1 or 2% damping. So ideally, I mean, this applies to sort of all of these damping schemes, Rayleigh damping, whatever kind of damping you're using for small strain damping. So ideally, Maxwell damping should be used only to provide small strain damping of less than 1 or 2%. And if you need damping higher than that, your fancy nonlinear constitutive model should be providing that higher damping. But that's the ideal case. But sometimes maybe there's structural components like a beam element or something that you want to use 5% damping for. So there's workarounds that you can use, like you could decrease the relaxed modulus, the zero frequency modulus. So that even with an increase in phase velocity, you can match your target frequency range of interest. You can keep the right phase velocity. And there's actually several geophysics papers where they discuss this and sort of like fine-tune their model to match to get the right phase velocity at a certain frequency. But again, I mean, ideally, it's not such an issue. It's not such a serious issue if you're sticking to 1% or 2% damping. So like with any numerical tool, new numerical tool, you've got to be careful when introducing it into analysis of civil structures, because there's life safety and maybe significant economic decisions that may be based on the analysis results. So in procedures for assessing the credibility, relevance of scientific computing simulations, they're often described in terms of verification and validation. I mean, I don't know why they would choose two words with V, but that almost sound the same. But anyway, those are the words that people are using. In verification, that typically involves comparing to numerical solutions, comparing your numerical solutions to closed form solutions. And validation is a little bit more nebulous, and it's really concerned with, okay, like, so you did your numerical implication right, but I mean, does this theory or mechanism you're using, does that really capture the real physical world behavior that you're trying to simulate? And to me, that's something, this validation is something that it would occur, over experience with many projects, and then looking at benchmarking case histories, that kind of thing. But verification part is a little bit more straightforward. So for part one, we're going to look at verification of Maxwell damping for linear elastic models. And when Maxwell damping is applied to linear elastic materials, the system is a linear viscoelastic constitutive model. So that's a fairly simple, well understood kind of theory. So there's many closed form solutions that are available. So we're going to look at stress strain loops for cyclic loading, spatial attenuation of traveling waves, and then we thought for civil engineering applications, time attenuation of decaying free vibration modes provide some useful test problems. So first, stress strain loops for harmonic loading. So these stress strain loops for cyclic loading, we can compare flak element behavior to the viscoelastic solution using it from the complex modulus. So again, this is a time history of stress and strain for particular elements cycled at a particular frequency and a particular cyclic strain amplitude. And shown here are in, let's see, the flak 3D results are shown in red there, and blue is the analytical complex stiffness solution. So we're looking at all these are at 5 hertz, different damping. You can see the stress strain loops match between flak and the analytical solution. And here are stress strain loops for various frequencies. So that's like an element test of the Maxwell damping scheme, which looks good. Then spatial attenuation of traveling waves. This is the typical problem that all these seismology and exploration geophysics codes use. They just do some pulse here. We're using a Ricker wavelet, and you just put that in at one end of a flak model, and look at some distance, see how that attenuates with distance as this wave propagates. And again, we've done that. But again, but for civil engineering applications, this seems like a kind of artificial. It's not a very satisfying. I mean, it makes sense for seismology, but does it make sense for civil engineering type things? So we thought for civil engineering applications that include buildings, dams, wharves, and tunnels, maybe a more natural verification problems would be time decay of various free vibration modes. And so we looked at vibrations of beams, cable elements, and for solid elements, we're looking at vibration of elastic spheres. And viscoelastic solutions to these problems can be obtained from the linear elastic solutions using the correspondence principle of Bland. So if you have a linear elastic solution to one of these vibration problems, all you need to do is plug in, take the linear elastic constants, and you replace those with the viscoelastic complex moduli. Okay, but it turns out there's one, this is maybe a little bit more detail than you need here, but it turns out there's a kind of theoretical issue here with these decaying oscillations. So solving these problems requires at least some less familiar aspects of viscoelastic theory. At least they were unfamiliar to me, which is, I guess, why I'm making a big deal about it. So steady state harmonic loading is described with a familiar, like, real frequency, and that works for steady state harmonic loading. Constant amplitude with time, nothing's changing with time. But material elements within a decaying vibration mode problem, they experience cyclic loading at a decaying amplitude here. Like, as you see, like, okay, this is the time history at a particular point in one of these decaying vibration mode problems. So it's not experiencing constant steady state harmonic loading. It's experiencing harmonic loading at a decaying frequency, at decaying amplitude. And these can be decaying oscillations. They can be described with a complex frequency. So you have your real frequency plus a complex term. And that complex term is accounting for the decay of the amplitude. So anyway, for a correct solution of a decaying vibration mode problem, you need to use viscoelastic modulus computed from a complex frequency, not from the real frequency. So we've done a bunch of these decaying vibration problems here. We'll just show one for shell elements. So this is a circular plate clamped at the outer boundary, and we're using linear elastics. We're starting from the linear elastic solution presented in this book by Sodell. And these are typical kind of like separation of variables problems where you end up with a whole bunch of different eigenvalues and matching eigenmodes. So those are vibration modes. And we're going to concentrate on the lowest frequency mode, which is this m equals 0, n equals 0 mode with the vibration mode that looks like this. And how you run this kind of problem in FLAC is you take the analytical solution and you try to excite exactly this mode. You don't want to have a bunch of different modes going at the same time. So you want to excite very cleanly the particular mode you're looking for. So we take that analytical solution and we initialize the vertical velocity of the node points, of the structural nodes, to the target mode shape. And then, these are structural elements, so they have a rotational degree of freedom also. So you also have to initialize the rotational velocities of these nodes to cleanly excite that mode. And then, so you initialize those velocities, then you run the simulation for decaying oscillations, measure the decay rate, and then you can check again that you've still got that mode. And so anyway, the computed damping and displacement modes closely matches the analytical solution. Damping is shown here; it's closely matching the analytical solution. So it's just an example of those kind of decaying vibration mode problems, which we've run a bunch of. So that was verification for linear elastic base model, and that was relatively straightforward. There's analytical solutions, lots of analytical solutions, but when we switch to nonlinear models, for elastoplastic materials, there are fewer, I don't know if any, closed form solutions for comparison. So instead, this verification and validation is a little bit more qualitative. So as a first step, we did some detailed inspection and observations on stress strain loops for linear elastic perfectly plastic models and for more sophisticated hysteretic type models. And as a second step, we did a sort of benchmarking analysis between Maxwell damping and Rayleigh damping for seismic loading of a simplified embankment model. So again, this is both qualitative and quantitative here. So we're looking at stress strain loops, and does the behavior appear reasonable as expected? And so that's the qualitative part, and the quantitative part we can do is how much additional damping is actually added to a base nonlinear model. And we want to check this for a range of shear strains, frequencies, and plastic yielding behavior. So first, we're looking at these stress strain loops for linear elastic perfectly plastic models like the Moore-Coulomb model. And sort of the base Maxwell damping behavior looks like this. This is 2% damping at frequency of 5 hertz. And but also, so on the right, we're showing for compatibility with Rayleigh damping. It turns off stiffness damping for the Moore-Coulomb model or these elastic perfectly plastic models when you're yielding. And the idea there is, okay, when a perfectly plastic model is yielding, it's producing plenty of own internal damping, so it doesn't need any additional viscous damping. So Joe has added this switch that you can have off when yield, if you want to have compatibility with how the the built-in Moore-Coulomb model is turning off viscous damping during yield. All right, so that's an elastic perfectly plastic model. And then we wanted to do some testing on a more realistic nonlinear model that has some hysteretic behavior. So what we've used for that, we're using, just trying to keep things as simple as possible. We're using the FLAC hysteretic model, in particular the sigma 3 hysteretic model. And we've done a fit to the Darendelli modulus reduction curve for clean sand, 1 atmosphere. And so that's the damping, that's the G over G max curve, which the sigma 3 hysteretic model is fit to. And that close fit to the G over G max curve gives this damping curve, which is actually a little bit higher than the Darendelli curve. But anyway, we're trying to make things simple, so we're doing a exact fit to the G over G max curve from Darendelli, and it gives this damping curve. And then you can see this model, we've shown stress strain loops here for different cyclic strains. So you see, like, okay, these strains with increasing cyclic strain, the secant modulus reduces, and you get more damping, a bigger area of the loop. So that's just the behavior of the sigma 3 hysteretic model in FLAC. Then we want to add various amounts of damping, Maxwell damping to that, and you can see here's 1%. So the hysteretic model is shown in blue. The Maxwell damping with Maxwell damping is shown in red. So 1% damping, 3% damping, and 5% damping. And again, as you mentioned, okay, for a nonlinear, if you're using a nonlinear model like this, you probably wouldn't use 5% damping, but because the model itself, the hysteretic model itself can handle that level of damping. But we just wanted to show that for comparison purposes. So that's individual stress strain loops. And I mean, that's the qualitative, say, picture. I mean, that looks pretty reasonable. But then we want to, like, do the quantitative aspect and, measure the actual added damping that Maxwell damping has provided. So we're using this typical, like, energy of this, computing damping from the area of the stress strain loop that's used in. So this is the typical calculation that's done in soil mechanics. So here, what we're showing is stress strain loops for a range of cyclic strains, and these particular results are at 5 Hertz, but we've done it for various frequencies, and you can see that in red, up here you can see the stress strain loops with Maxwell damping. So we've done that for the hysteretic base model as shown in blue, and then if you add 2% Maxwell damping, the total damping is this red line, and then for 5% Maxwell damping, that total damping is this purple line. So that looks pretty reasonable, but let's sort of subtract out, and let's just look at the difference in added damping we're getting from Maxwell damping, and that's shown here. So this is computed by subtracting out the hysteretic model damping. So this looks like for 2% Maxwell damping, I mean, this is looking great, except when you're getting a little bit of extra damping at these very high cyclic strains. And again, let me just back up here. I mean, but in that range, you're at 30–50% damping. So I mean, a little bit of extra damping is not such a practical concern there. So this has sort of, this isn't exactly the ideal behavior you would want, but the practical significance of that is pretty small. But I want to note that this is a complex nonlinear system. It's not linear viscoelasticity, so some deviation from ideal and perfect behavior at larger strains, should be expected. I mean, we're not in Kansas anymore. This isn't linear viscoelasticity. All right, so the next sort of validation verification problem we looked at is benchmarking against Rayleigh damping for nonlinear analyses. So again, Rayleigh damping, that's the most traditional, most commonly used tool to provide small strain damping for nonlinear deformation analyses. So we're going to compare against that, but you know, sort of there's a sort of problem here that okay, we developed this new damping because Rayleigh damping has some issues, you know, and so we have to be careful about those issues. So for Rayleigh damping, as you mentioned, the frequency range of constant damping is relatively narrow, and outside of that range, you have very high damping. And also, there's these spurious body forces produced by particle velocity. And both of these issues with Rayleigh damping must be taken into account in these benchmarking analyses. So, so our benchmarking problem, we've come up with this sort of a 3D cone as a proxy for a generic embankment dam. And we're doing this analysis with a linear elastic, perfectly plastic model, the Coulomb model. So we've got a cone height of 100 meters, 2-to-1 slopes, shear wave velocity of 500 meters per second, 35-degree friction angle. And then we're applying earthquake shaking to the base of the cone using rigid base input. And we're applying shaking in all 3 directions. So this benchmarking problem was performed for 2% and 5% damping. And the Rayleigh damping, to try to you know, set the Rayleigh damping right here, we're using Rayleigh damping with a center frequency at 2.1 hertz to match the first horizontal mode of the frequency of the embankment. And you know, using this simple embankment shape and a simple perfectly plastic constitutive model, it gives you know an embankment model with a distinct, well-defined fundamental frequency. So this should limit the effects of the frequency dependence of Rayleigh damping here. So here's our 2 damping curves. Maxwell damping, we've got this broad range of nearly constant damping, and damping drops off. But Maxwell damping, Rayleigh damping, we're setting it at this 2.1 hertz frequency, which is the frequency of the embankment. And you know, right at that frequency of the embankment, yeah, Rayleigh damping and Maxwell damping are pretty much the same. And we're also using this off when yield option, which turns off Maxwell damping when you have plastic yielding. Because you need that to be compatible with the flax built-in Rayleigh damping. All right, so as far as comparison metrics for this problem, so the primary metric for this seismic shaking problem is the computed permanent shaking-induced displacements. So we're looking at vertical displacements, shown here, vertical displacements of the crest, and then X horizontal displacement, we're looking at negative X displacement, positive X displacements, and then Y horizontal displacements, negative N horizontal displacements. And then, you know, we also looked at peak accelerations and velocities, but we're just going to show the displacements here. And here's a comparison. So I should also mention, okay, we're running this analysis case for 4 earthquake time histories, and we're using far field motions, you know, that were recorded very far. So we're earthquakes that were very far from the recorded record. Seismic instrument where the earthquake was recorded. And the issue is if you have a near field motion, often those have very high velocities, and these fictitious accelerations due to Rayleigh mass damping could be significant. So we want to avoid that, so we're using these far field earthquake input motions. And how we're doing this comparison is you know, these metrics of vertical displacement, horizontal displacement in 2 directions, positive and negative. We're plotting those on this comparison figure. So we've got Rayleigh damping displacements on the horizontal axis and Maxwell damping displacements on the vertical axis. And you know, if these 2 forms of damping are giving the same result, we should expect everything to plot along this 1-to-1 line. And that's pretty much true for the horizontal displacements. We are seeing a little difference in displacements at the for the vertical displacements, but you know, you can see just at this cone model right at the tip, there's kind of a mesh sensitivity issue. You don't have a lot of elements up there, so it's clearly going to be sort of sensitive to things. So maybe this wasn't the ideal sort of comparison problem. But on the other hand, maybe that's a good thing, because I mean we are seeing a difference here, and you would expect. I mean, these are drastically different kind of damping models, so you would expect some kind of difference at that in that small scale like that. So this is these results are for 2% damping, and I think you can say, looking at these results, that well, you can imagine you're going to run some one of these analyses. The first thing with Maxwell damping, the first thing that your project manager is going to ask is, okay, is this newfangled Maxwell damping going to give me some drastically different number than Rayleigh damping? And I think what this shows is, no, you're not going to get drastically different damping. I mean, you're not going to get drastically different results with Maxwell damping for this kind of benchmark problem. So that's 2% damping. This is 5% Maxwell damping. All right, so a few sort of comments and observations before we switch over to Joe. So again, Maxwell damping, it's a new damping option in FLAC 3D. It has a number of advantages over Rayleigh damping, but with like any numerical tool, you got to be very careful when you're using it in analysis of civil structures, where it's not just some academic exercise. There's life safety issues, significant economic decisions may be based on these analysis results. And we've done considerable work on verifying Maxwell damping in FLAC 3D, but still to date, there's been little experience using this Maxwell damping in civil engineering applications. And that's in contrast to Rayleigh damping, where we've got maybe over 60 years experience using Rayleigh damping on these in seismic analyses. So whenever possible, analyses incorporating Maxwell damping, you should spot check them, benchmark them against Rayleigh damping analyses. So Joe, you want to take over?
Maxwell damping has been implemented in many elements. For example, for FLAC 3D, FLAC 2D, and 3D. And it has been implemented for solid zones, FLAC 3D, and blocks for 3D, and contacts for 3D, and also for structure element, as well as structure deformable links. And very recently, we updated the implementation for non-linear behavior, and as Ethan already presented. So for the command, for example, for FLAC 2D and 3D, just zone, dynamic, damping Maxwell, and 6 parameters, and some flag. Okay. For 3D, similar block, mechanical, damping Maxwell, and parameters, and also flag for zone only or contact only, and for structure element similar, and also for structure deformable links, similar 6 parameters are required. So people were wondering how to input parameters. Usually you do not require calibration. You just have a figure what the target damping ratio would be. For example, 5%, we already have the input parameters calibration for you. You just directly use these parameters, okay? But if you really want to play with these parameters, a simple fish or Python script, or even a simple Excel spreadsheet will do the job. So anyone want to, have this Excel sheet, so you can just input this yellow highlighted parameters, and then you can adjust, and you can see the figures. For example, for the figures on the right, so we have 5% target damping ratio based on these input parameters. So we can see that almost perfect constant damping ratio between 0.05 and 25 hertz. Okay. Right now, I will show some applications. The first application is a 1D side response. So we have a uniform soil column, okay, about 30 meters thickness, and below this soil is a half space rock bed. So we consider the rock bed is a component base. So we compare result with 3 scenarios. The first one, we using deep soil using a constant viscous 5% damping. So this was based on frequency domain. In the second case, we using Flex 3D 5% Rayleigh damping. So 5% Rayleigh damping is only at 2 frequencies. One is a 2.5 and another one is 12.5, because the natural frequency of this pure soil is 0.5 hertz. Okay, and then the last scenario, we use a Maxwell damping 5% target damping between half and 25 hertz. So we input 12 different outcrop motions. So this result is the first 6 input motions. So for the Maxwell damping is a red line. For Rayleigh damping is a blue line, and deep soil viscous constant damping is a green lines. So if we look at these 6 results, we can see that the Maxwell damping actually is closer to the deep soil viscous result. So here we just make deep soil viscous as a benchmark, result. Does not mean that this the physically correct result. Okay. And if we look at the Rayleigh damping, it's some result is higher than the other 2, yeah. But usually we didn't find any significant phase shift for these problems. Okay, and this another 6 input motions. Okay, similar result, but I want to take out one result based on the Nahani input motions. Why I should pick up this one? Because this motion have a lot of high frequency content. So if you look at the result, we can see that Rayleigh damping have much lower spectrum, compared to other 2. Okay? Maxwell damping is much, close to the deep soil viscous. Why the result is like this? Because Rayleigh damping is overly damped at high frequency content. Okay, but of course at a low frequency, because the initial effect, is not so important. But high frequency, we can see some differences. Okay, but the most highlighted difference is the calculation cost. Okay, the allowable dynamic time step for 5% Maxwell damping is more than 10 times of the Rayleigh damping. Okay, that means that the calculation time for Maxwell damping is only maybe less than 10% for this simple one-dimensional side response examples. So next example is a 2D side response. Okay, so here is a soil profile. We have Alameda, old Baymart, and young Baymart, etc. And then we using free field for this 2D analysis. And then we input 5% target damping ratio for both Maxwell damping and Rayleigh damping. So the input command just very simple, just one line. Just I present here. Okay. Here is some selected displacement history between Maxwell damping and Rayleigh damping. So we couldn't see any significant difference between these 2 damping schemes. So almost the same. And if we look at the final shear strain distribution are almost the same. So again, the most difference is calculation time. For these 2D examples, the allowable time step for Maxwell damping is 12 times of that of Rayleigh damping, and but the result are almost the same, but the calculation time is much lower. So for 1D and 2D side response, because this model is not too big, and then the difference only 10, it's maybe not big deal. But if we have some very large 3-dimensional soil structure interaction, because the stiffness of the structure usually is much bigger than the soil. So if we use Rayleigh damping, the allowable time step would be very small. Okay, if the model is very big, for example, millions zones or millions elements, the calculation time could be not practical at all. So here is the examples I using Maxwell damping for this soil structure interaction. Here is a video to record some displacement history and the acceleration history, and also the contour of the displacement for the model. So I only show half of the model. Okay. So the running is quick. Okay, but the big difference is this. So the actual calculation times depends on your hardware. But if we assume that this soil structure interaction need calculation for 8 hours, and then if we use Rayleigh damping for 5% target for this soil structure interaction, that would be 1,000 times required for the calculation time. If we assume 8 hours for Maxwell damping, and then for Rayleigh damping, about more than 300 days. Okay, even for very small target damping 0.2%, and then the difference would be 112. With a factor of 112. So suppose that you would not, run this model for 300 days. Yeah, it's not practical at all. But for Maxwell damping, things totally changed because it only required 8 hours. For example, that's less than over now. That's totally practical. Okay. So here is some summary for this presentation. Maxwell damping has been implemented from version 9 and have good performance in verifications and validation, and overcomes the main shortcomings of Rayleigh damping. And also most important is make very large 3-dimensional soil structure interaction practical, because the allowable time, dynamic time step is quite different. But at the last, just be aware of the advantages and disadvantages of this Maxwell damping, and also be aware of the application range. So here is some references for this presentation, and thank you very much. For any question, just ask.
Great. Thank you, Ethan. Thank you, Joe. So we do have some questions. Okay, so the first question, can Maxwell damping be used with more coolant to do seismic time history analysis for reinforced soil walls? Is the phase velocity issue significantly affecting these results?
Yes. For the second application, 2D set response, I use a molecular model combined with Maxwell damping, and the result is quite good. I didn't see significant phase shift for that example, because for typical soil deposit, the natural frequency is not so high, so that is not an issue.
Yeah, and I'll just chime in there. Is like, okay, I don't think that. I mean, if you're using a more Coulomb model, you don't. It has a lot of damping, plastic damping itself, so you don't need more than 1 or 2% Maxwell damping. So in that case, this phase velocity issue. I mean, if you get up to super high frequencies, yes, you have maybe a few percent increase in phase velocity. I don't see that as a practical issue.
Great. Next question. Given that the Maxwell damping is recommended primarily for damping values below 1% with regards to the phase velocity consideration, would there be any significant drawbacks relying solely on the hysteretic damping in this range?
Well, yeah, I mean, I guess that those hysteretic models, okay, it has very low, the damping from those models is very low at small strain. So usually you do need some additional damping.
Next question. Thank you for the presentation. For the conical embankment example, what is the main advantage of using Maxwell damping? Was it to reduce the runtime, larger time step? If so, how much larger time step were you able to use Maxwell damping for the conical embankments?
Yeah, well, that's funny. Okay, I figure I didn't even look at. I wasn't even interested in the runtime there. I mean, that was just purely a I was just trying to come up with something that represented that was a proxy for our kind of typical applications. So that was purely a benchmarking problem. So I'm afraid I didn't even look at the. I was more interested in are the displacements comparable? But yes, I mean, it would obviously have a much greater runtime than the Rayleigh damping. I mean, a lower runtime than the Rayleigh damping model.
Thank you. Can you give us a hint on how to select the extreme frequencies in common engineering cases? For example, embankment dam, shallow foundation, etc.
Usually, you need to estimate the natural frequency of the model, okay? And for Rayleigh damping, we usually cover the target damping at this natural frequency and some factor of that natural frequency, for example, 5 times or 3 times. And for Maxwell damping, usually we need to calibrate the almost constant damping between that 2 frequency, or a little bit extended, range to cover that frequency. That's my practice.
Yeah, and I think one of the features I like about this Maxwell damping is like there's so many I've had so many endless discussions and debates about what exactly the center frequency you should use for Rayleigh damping is, because you have such a narrow frequency range of constant damping. So with Rayleigh damping, you really do need to know what frequency your structures have. And I think with Maxwell damping, it's much less important to actually know what frequencies you'll have. But I mean, of course, you should have some idea. And it's not, and I should mention, it's not just the frequencies of your actual structure, but I mean, it's also the frequency content of your input motions too that you need to take into account.
Great. Next question. Have you also compared with local damping?
Yes, I also compared the local damping for that one-dimensional set response, but I did not present here. My results show that local damping is not suitable for dynamic analysis and quite different with other dampings. So local damping is not a selection for dynamic analysis in Flex 3D.
Yeah, I think I've had similar experience with local damping.
Great. There's just a general question that I can answer regarding the recording. So yes, we recorded the webinar and it will be available on our website, and anyone who's registered will also get an email once the video has been post-edited and is available. So you can watch it at your own pace. And then the last question I have is, Was a deep soil verification a total stress analysis or an effective stress analysis?
Oh, because for that example, there's no water involved, so they're the same thing.
Oh, sorry, and we just got a last question. In the comparison between Rayleigh, Maxwell, and deep soil damping, we observed that Rayleigh damping overdamps on high frequencies. In the formulation, the damping ratio is practically constant over an intermediate range of frequencies and higher values for lower and higher frequencies. So in the example, why didn't we observe overdamping with Rayleigh for low frequencies?
Oh, because for low frequency, the inertial effect is much significant, than the frequency effect. So generally, that's not big deal at low frequency.
If there are any other questions, we've got another minute or two. Okay, so thank you everyone for joining us today. Thank you, Ethan. Thank you, Zhao. I just wanted to let everybody know that, just a reminder that Maxwell damping was added to version 9 of FLAC 2D, FLAC 3D, and 3DEC. So if you're interested in playing around with it yourself, if you'd like to update your software, or if you'd like to get a 2-week trial, please contact us through sales, S-A-L-E-S, at ITASCAsoftware.com. sales@ITASCAsoftware.com, and we can either get you a quote or we can set you up with a free 2-week trial. Great. Thank you very much for joining us. Thank you guys for the presentation. That was fantastic. We will post the video to the website and you'll get an email if you've registered. Take care, everyone, and have a good day.